Okay, well, we proceed on to some easier problems. We've got another problem, same situation, maybe. We don't specify in the problem, but you're given that a car starts on a ramp, starts up a ramp with some initial potential energy. It's released, and that potential energy sooner or later changes to kinetic. So the car then goes up the incline and ends up at rest after 100 centimeters. Okay, so start with potential energy, 10 joules, released up a 30-degree incline, and there's a picture of the triangle involved. It's supposed to be a right triangle. I missed that right triangle by 20 degrees or so, the right angle. But it's supposed to be a right angle there. Just a quick sketch. You got 100 centimeters in the hypotenuse, 30-degree angle here. You should understand that this cosine of the sine of 30 degrees is 1/2, and you should be able to derive that using triangles. Simple derivation, everybody should know. So you have 30-degree angle here, 100 centimeters here. You easily determine that the rise is going to be 50 centimeters. So if this thing gains the gravitational potential energy, it would gain through a 50 centimeter rise. It does have a 50 centimeter rise, but so if we're given all this information, we want to find the mass of the car. Okay, well, the change in gravitational potential energy is going to be the 10 joules that we lose in potential energy here. So the change in gravitational potential energy, of course, is mg times the change in your y-coordinate, the change in your vertical coordinate. That's got to equal your 10 joules. Since the initial sum of potential and kinetic energies is equal to the final sum of potential and kinetic energies, because implicitly or explicitly in the statement of the problem, there are no dissipative forces. The only forces acting again are going to be the source of your potential energy here and the gravitational forces. Okay, since then the total energy is the same at the beginning and end, your final potential energy is equal to your initial potential energy, and that got smudged. So let's write that in. And all this is the reason that your gravitational potential energy will then be 10 joules. Because your final potential energy is all gravitational, that's your gravitational potential energy, and that's got to be equal to your initial potential energy. Gravitational equal initial. You know G, you know delta Y, 50 centimeters, you know this. You can solve for the mass. So you can do that. That's not going to give you any trouble. Another question, you approach, you start at the top of an incline at 10 meters per second, accelerate along the incline at 1 meter per second squared, and end up at 20 meters per second. How far did you go? Well, we've been doing a lot of things with energy conservation. If you knew the angle of the incline and all the forces involved, you could solve this with energy considerations, but you don't know those details. You know if there's friction, air resistance, or whatever, but one way or another you're accelerating at 1 meter per second squared. Well, this gives you a simple problem in motion. Initial velocity is 10 meters per second, final velocity is 20 meters per second, your acceleration is 1 meter per second squared. That's enough information to find how long it takes to get there and how far you have to go to achieve this speed. You end up using what I usually call the fourth equation of uniformly accelerated motion. Final velocity squared, initial velocity squared, plus 2a times your change in your position along your path. And we know this, we know this, we know this, so we can solve for this. And this is how far you go. Generally, we would let x naught equal 0. There's no reason not to in this case. So if we do that, we just get the position x. But one way or another, we get the difference between this position and this position, which is the answer to how far. And of course, it would be very easy then to calculate the time it takes to get there. Okay, another situation, we've got a ring with a 10 Newton force at 37 degrees, 20 Newton force at 143 degrees acting on the ring. We want to know how much force, or exactly what force, magnitude, direction, or vector force required to balance these two forces. Well, we find the resultant of these two forces. Now the resultant, of course, we could get by a parallelogram. Okay, well, the parallelogram I have is up here somewhere. This should be equal and opposite to whatever we get from the parallelogram. And looks like it might sort of be. But I just kind of drew it there. We know it's going to be kind of down into this quadrant just because of relative sizes of these forces and the angles. Very straightforward to calculate the sum of these two forces, which I do using the I and j vectors. The first force is 10 newtons times the cosine of 37 degrees times the I vector, plus 10 newtons times the sine of 37 degrees times the j vector. Second force, well, same thing, I'm not going to read it to you. It's this magnitude times the cosine of the angle times I, and the magnitude times the sine of the angle times j. So the sum of the two forces, well, I write out this times I plus this times I gives you all this times I, and this times j plus this times j gives you all this times j. And I think here are the i's and here are the j's. You do that, you do the arithmetic, and it's pretty easy to do the arithmetic. I like to use 37 and 53 degree angles, and angles of 37 degrees with one axis or the other, because they're really easy to calculate with, because the cosine is 0.8, very close to 0.8. The sine is 0.6, or very close to 0.6. Using those numbers, it's easy to calculate. If I did it right, I see that the I component comes out negative 8 newtons. Just calculate this thing here. And the j component comes out to 18 newtons. Negative 8 newtons here, 18 newtons here. There's your net force. Well, this is the sum of these two forces, and the force you need then to balance them is the equal and opposite to that force. So it's going to be the negative of that sum. And yeah, I did close the parentheses. Okay. And of course, you do the negative of that sum, you're going to end up with plus 8 newtons times I, minus 18 newtons times j, and if you need to, then you can use the Pythagorean theorem to find the magnitude of the net force, and you can use the inverse tangent of the y over x component with a little bit of common sense, because your x component happens to be negative, and calculate the, now actually your x component is positive, but anyhow, you calculate the angle here. Okay? Now let's see, I think, nope, okay, we did have stuff here. Next problem, you've got something moving, a block moving in some direction, and a force at 60 degrees to the direction of motion. And you want to find how much work is done by the force as you go a certain distance. Well, force is 50 newtons. It's at 60 degrees to the direction of motion, meaning you have a parallel force here and a perpendicular force here. Only the force parallel to the direction of motion, only the component of the force in the direction of motion does work. So your parallel force is 25 newtons. This one turns out to be about 43.4 newtons or something like that. And I know the numbers perfectly well, but it's getting late. Okay, so anyhow, those are your forces. This one doesn't matter. This is one. This is a component that does work. So the component in the direction of motion is this, 25 newtons. The work is that parallel component times your delta S, your displacement in that direction. And the displacement is said to be 20 meters, so you have this calculation. Very straightforward problem that reinforces the idea that only the parallel component does work. Only the component of the force parallel to the direction of motion will do work. Okay, here we have a situation where you start a ball upward at some initial velocity. So the ball is here, it ends up here 20 meters higher. Question then is, well, if you start out twice as fast, how high does it go? Well, there are several ways to solve this problem. You could go to all the trouble of using the equation of motion to actually find your V0, and then use the equations of motion to find how high you go if you start with 2 V0. You'd have to do all the numbers and stuff. You don't have to do that. You could. On a test, I wouldn't recommend it because it's going to take a lot longer than reasoning it out. But if you have no other option, that will work. It'll probably cause you to come up short in time. Okay, well, the way I would like to reason it out, there are two possible ways. It's going twice as fast. If you're going twice as fast, then it's going to take you twice as long for the acceleration to bring you to rest. Okay, for the downward acceleration to bring you to rest. Because acceleration is the same in both cases. The acceleration is the rate in time, rate with respect to time at which the velocity changes. If you got twice the velocity, it's going to take you twice as long. Also, if you got twice the velocity, then you have twice the average velocity. So you have double the average velocity acting for twice as long. It's going to give you 4 times as far. So you're going to go 4 times as high, you're going to go 80 meters. So we get that that's 80 meters. Now you would have gotten the same thing if you'd have done this, but this is much more elegant and much more insightful than just plugging into a bunch of equations. Okay, alternatively, if you're going twice as fast, you have 4 times the kinetic energy. If you've got 4 times the kinetic, now why do you have 4 times the kinetic energy? Because kinetic energy is 1/2 mv squared. It's proportional to v squared for a given mass. And if v is twice as great, v squared is 4 times as great. You square the quantity 2v, you get 2 squared times v squared, you get 4v squared, okay? So, anyhow, you have 4 times the kinetic energy, which gives you 4 times the potential energy at the top as your kinetic energy and kinetic potential energy reverse. Okay, we're implicitly, again, assuming that there's no air resistance or other dissipative force acting. So you got 4 times the potential energy at the top. Well, 4 times the gravitational potential energy on the same mass requires you go 4 times as high. So again, you're going to have to be up at 80 meters. And you don't have to do any numbers for this and this. No numbers except 2 and 4. So you don't have any complicated calculations. Here you have calculations that aren't all that complicated, but they're a lot more complicated than what you've got down here. Didn't need to do that, but it won't hurt anything. Okay. Now you got a beam rotating at 6 radians per second. And you've got a block sitting on the beam, a rider on the beam, okay? And the first question we want to answer is, and what is the first question? What question did I just answer here? Yeah, the question here is, at what distance from the axis is centripetal force equal to the weight of the rider. So that's the question we're trying to answer here. Well, you see that this is talking about a centripetal force on something with mass. So what is a centripetal force on a massive object at a given distance from the axis? Well, at distance r from the axis, your speed is omega r, centripetal acceleration is v squared over r, and you should understand both of these completely. So your centripetal force is the mass times your centripetal acceleration, mv squared over r. Well, we want to know where that is equal to the weight of the rider. So we set this expression, mv squared over r, equal to mg, centripetal force equal to the weight of the rider. Mass divides out. We solve for r. We see that r is v squared over g. Now if you have, and of course, v is r times 6 radians per second. So actually we've got a little bit more work to do. If we want to get this in terms of omega. Okay. However, we could have calculated v here, and that's in some ways a sufficient solution. If we want this in terms of omega, then we're going to have an r squared omega squared over g here equal to r here, and then we're going to get, I believe, omega equals g over v squared. Doesn't seem like that'd be right. Maybe it is. Anyhow, that you can work out very easily. There's another question that I thought I was answering and wrote this down before we all realized that the question I put up in the chat wasn't completed. Went back to the original question, realized that the question was actually, at what distance will the rider no longer slip? Okay? And actually I should have said at what maximum distance will the rider not slip. But we'll see. Okay? So, your centripetal force, in order for the rider not to slip, must be less than or equal to the coefficient of static friction times the rider's weight. Because if it's greater than that, the force due to friction is not going to be sufficient to supply the centripetal force. If this is too big, you're not going to get the centripetal force from the frictional force. Frictional force will not be sufficient to hold you in that circle, and that's when you start to slide. It will not be sufficient to hold you in your circular path. Okay? So we solve this equation. First, writing centripetal force as mv squared over r. And then we solve for the distance r. And it's very straightforward to solve this for r. It's mv squared divided by mu s mg. Masses divide out, we get v squared over mu sg. And that's the answer to our question. So we can easily determine the maximum distance and for r greater than or equal to this, the centripetal force is going to exceed, something wrong with that. Now you can sort it out. There it is. Okay.